coenzyme A. I would somehow have to put it on here, which would require a thiolase. That's a lot of work. It's just easier to depropate than repropate, changing the configuration.
For an L configuration, doesn't the OH have to be on the left? So that H has to be.
There is no OH.
But what
It
do
just
you-
has to be whatever the functional group is on the last chiral carbon. So, sorry, I said that this, oh, I said this was the D. Sorry, this is the L. So the D is this one. You're correct. That's D. So the L would be on the other side. Okay? So, but essentially what I'm doing though is I'm just switching these two, because that's the easiest. Even though when I redraw it, it's going to look like I switched these two. I'm really just switching those. All right, so that's our isomerase. So now we got the right configuration, L. So then you're going to see the last step is going to be what? We're going to react it with coenzyme A, which we're going to learn a little bit about later in one of the later chapters. And so what that's going to do is basically they're calling it a mutase, but it's another isomerase. So what we're doing is we're essentially moving, right, this carboxylate unit to that carbon. Okay. So again, they're calling it a mutase, but it's just an isomerization. So we're going from the alpha carbon to the beta carbon with this. All right. So we're going to take that, and then with the mutase, we generate. So now we got this guy. And so now what's the advantage of this with the thiosuccinate? Right. We know that succinate itself can be placed directly in the citric acid cycle. And so we're going to see that there is a lot of biological use for this. So now that we took something that could not enter the cycle, the C3 unit, and we've created something that can. All right. Let's talk about some other things that we have issues with. Is there any other questions on this? How about if we have a unsaturated fat? So again, I'm just making this up, but this goes on and on. Suppose I have this one. I don't think that's in the right place. Hold on. It's got to be over there. Sorry. Because usually the unsaturations come in specific units. So what's going to happen here when I try to digest this fat? Well, first, nothing abnormal, right? Because it is a fatty acid, so I'll convert it to the coenzyme A. And then it's going to go through beta oxidation, right? So I'll lop off this C2 unit. Then I'll lop off this C2 unit. All right. Then I'm going to get to this unit now. All right. So if I lop off these two, that's one entry. I lop off those two, that's the next entry into the citric acid cycle. I then am left with, I think I did have it. Let's see. Let me draw it. Well, it just matters because there is a certain configuration. So what I want is that. So let's see, C. Right, so I did have it right the first time, sorry. Okay, so now I'm left with this. All right. Now this one I can't go forward. all right? Beta oxidation can't happen. But I already had the alkene there, so therefore I'm going to do what? What am I going to do? Isomerize. Okay? So I'm going to isomerize this. So the first thing I do is I isomerize. So that gives me this. But I still can't use it. So what else has to happen? An additional isomerization. Because this is just an isomerization of cis to trans. Right? So I got cis, I'm going to go to trans. But then remember, this is the alpha, beta, gamma. I'm now going to isomerize this to that. So I got alpha, beta, gamma. So I'm going to do two sets of isomerizations. I'm going to isomerize it from a stereochemical perspective. It's going to go from cis to trans. So I'm converting diastereomers. And I'm going to convert regioisomers. So it's going from, in this case, a beta-gamma trans to an alpha-beta trans. All right, so now another organic chemistry question. What's the driving force for this reaction? So I'm not even worried about, don't even worry about Le Chatelier's principle at this point. Chemically, why is it preferred to be this molecule than it is to be that molecule? There's one, so we got conjugation. We know the conjugated pi bonds are more stable than unconjugated. So that makes this better than that. Right? There's a drive towards conjugation. Conjugation, right, is a thermodynamic well. So why then is this better than that?
Resonance?
No, there's no resonance there.
Isn't the trans just a more
Yeah, because they're all
straight
on the
line, so
opposite
it's
side.
sterically better?
Sterically, all right, not necessarily a straight line, but sterically it's better, right? Because with cis we have what? Steric congestion, right? We have bumping into it. In other words, we got these two large groups, they're geometrically close to one another. So there's repulsion, sterically. If I make it trans, then I remove that steric repulsion. Right? So they're the two driving forces for this. So this is, like I said, thermodynamically very easy reaction. All right, let's take another example. Let's say that we have a polyunsaturated fat. All right. So in a polyunsaturated fat, what we have at some point is something that's going to look like this. And usually with a polyunsaturated fat, there's an additional cis unsaturation up here, but we're going to take care of that by that mechanism. So again, what's going to happen is we're going to move down, and then we're going to get to here. So that's where I want to start, right? So we're going to move down. When we get to this guy, this goes into operation, all right? We're going to convert that to the trans that's conjugated, then we can move forward until we get to now this system, all right? So that's where I want to pick up. Suppose we have something that looks like this. Okay. Now we got to take care of that. Because the problem is, even though this is in the trans, right? The problem is, that's not going to get hydrolyzed there. right? If we try to do a hydrolysis reaction here, even in organic chemistry, there's a good chance it's going to go there and not there. So we've got to work our way around that conjugated alkene or diene. The way we're going to do that is we're going to basically react this with a hydrogenase. In fact, I think it's NAD based. Let me check on that. It is. So I'm going to take this, I'm going to react it with NAD. H plus H plus. So we have two options here. The easiest option would be, chemically speaking, if we could hydrogenate this and not that. But unfortunately, that doesn't work that easy. What's going to happen is that instead of doing, so again, going back to organic chemistry, when we had a diene system, we can either do reactions 1,2 or 1,4. All right? This undergoes a 1,4 hydrogenation. So what happens is that we add hydrogen, but we don't add it across the double bond, we add it across the entire diene. So we get this. So again, remember, here now is my new alpha, beta, gamma, delta. So here's the alpha, beta, gamma, delta. So now I've done a 1,4 addition of hydrogen. So the hydrogen's adding at the alpha position and the delta position. All right? But now this really isn't a problem because it's already enough.
Why isn't that a 2,5 addition of H?
Well, I'm not counting this. I'm just counting where the diene is. I'm just looking at this diene. Right? So I got 4 carbons. Okay? So I can either add individually or I can add at the ends. All right? So this adds at the ends. But if I generate this, all right, even though it looks like it's an extra step, I already have the mechanism there. Because that's this. Okay. So now, again, I just do an additional isomerization. So again, I have an isomerase, which then is going to give me this. So now this is my alpha, beta, gamma. And so now that can go through beta oxidation. So that allows us now, we've seen the 3 ways to sort of accommodate the sort of 3 peculiarities in fats that you may consume. All right, if you consume an odd number, like I said, if you eat nuts or seafood or whatever. If you're consuming either unsaturated or polyunsaturated fats, they can all eventually be accommodated to pass through the citric acid cycle. So that's the whole point of that. Sure.
What are the best types of fats unsaturated?
Well, yeah, your unsaturated is your best because that's your highest energy. Right? For each unsaturation, that's less energy than you have in the cycle.
Does it have anything to do with how long it takes for it to get to this?
Well, it's extra steps. But I mean, really what it comes down to is energy. So why would an unsaturated fat be worse in energy? I'll throw the question back at us. Where are you losing energy if you have an unsaturated fat? Let's just use the first example. Suppose I just have one site of unsaturation at cis. Why am I losing energy here?
Because you have to convert it over to trans?
I do, but thermodynamically that's good. So I'm not losing energy there by making it trans. So where am I losing the energy? If I have a saturated fat, how do I make it unsaturated, right? I know that I need this intermediate for beta oxidation. And I know I can make this from this, right, by the isomerization, which is thermodynamically in the right direction. So where am I losing my energy? Right? I'm comparing if I have a totally saturated fat to a fat that has 1 unit of unsaturation. Where am I losing the energy?
Oh, the hydrogen
What's that? Which one?
the compound.
No.
I mean, you'll have to, is it reduce it? Or oxidize it? You have to throw in H's onto it, right? And you'll
If I
get
throw
those.
H's onto it, I have to,
I forget the technical term for it, but you're going to use NADH onto
exactly. Well,
And you
am
got
I
to
going
reach
to
it.
use it or am I going to make it?
That's a good call. Yeah, you're going to make it.
Going to make it, right? I have to generate this unsaturated
Yeah, I'm not really here
intermediate.
today.
I got to make NADH,
Nice.
right? I got to dehydrogenate my saturated acid. And if I make NADH, what's going to happen to that NADH?
It's going to compete with glycolysis.
Well, no. What it ultimately, what's the NADH going to, in theory, do?
It's going to build up in concentration.
It should transfer electrons to oxidative
Yeah.
phosphorylation, but
Right. Well, it's going to transfer electrons, and that's going to make 2.5 equivalents of ATP. So if the unsaturation is already there, you're losing 2.5 equivalents of ATP for your whole acid. Okay? So each unsaturation. Now, all right, here's the next one. Suppose we got the conjugate. Again, what did I have to use? I had to use an L equivalent of an ADH. So not only did I not generate an equivalent like I did over there, now I'm actually using one that I already generated. That's another loss. Okay, 2.5 equivalents of ATP.
so you lose 5.
So now, right, if I have a conjugated diene, I lose 5 equivalents of ATP
Because
So
we're
that's
making NADH or because we're using it?
because I'm using it, right? I have to use this NADH in order to prep it so it can go into the cycle. Okay? Which means if I'm using it here, that means I can't be generating ATP elsewhere when I do the oxidation.
So it's definitely going to be a test for
It could be, but you can't use it. All right? But yeah, so the more unsaturated the fats are that you're eating, the less energy you're getting out of it. There's not as much energy content in it. Okay.
Even though they tell us it's a healthier fat to eat.
What's that?
Even though they tell you it's a healthier fat to eat, unsaturated fats.
Yeah. Well, you're just getting less energy out of it.
So
Okay.
I guess that we have to
All right.
because then you have to make
We're not going to get done chapter 17 today. All right, but we will definitely get done. What do you mean, yes? You told me you wanted to commit to the test.
it. Yeah, but
All right.
it's lower we are.
Yeah, so you are, that means that we're going to lit up on the final. All right, last thing I just want to talk about very quickly, okay, and then, we'll sort of end it here. Regulation in the cycle. All right, so again, we kind of went through that gory chapter 15, where we talked about regulation. But again, just very quickly, all right, parts that we're going to regulate as far as in the oxidation of the fatty acids. So where I want to concentrate is, what's going on in the liver, okay? Because that's where you have the most, options when you do with the fatty acid. So if you're looking at things that are regulated, we're kind of looking at the following. The first thing that's going to regulate it is location, okay? No matter what cell is involved. Because where's the fatty acid originally in the cell? Comes into the cytosol, right? Comes in, okay, so we transport the fatty acid in. Where's it got to go to make energy? Right, it has to go to the mitochondria. So unless it's small, all right, we got a barrier there. We got to a transfer battery. So one of the things where there's going to be regulation is how quickly you're going to transfer it into the mitochondria. And that's going to rely on, right, the carnitine, right? Its availability, all right? And so that's regulation sort of by site. Okay, we can exclude, the reactions, reactants from the reactant zone. All right. Some other regulators, okay? A high, let me just write these down, and then you're going to be able to guess what's going on here. Maybe not with the specific enzyme, but let's say that we have a high NADH, NAD plus ratio in the mitochondria. All right. So, would you expect that to accelerate the process or retard the process?
I'd say slow it down.
Yeah.
You're saying you have more NADH than
Right. If I have more NADH than NAD, that's telling me what? I'm basically potentially energy rich. I'm not consuming this, right? Because this, right, is going to get, transferred, it's going to lose its electrons, it's going to make ATP. So if I have a really high ratio of this to that means I'm on the energy rich side. All right? So specifically, right, this inhibits the beta hydroxy acyl coenzyme A dehydrogenase. So in other words, the enzyme that's responsible for making this alkene is going to be inhibited by a high NADH-NAD ratio. Right? And that makes sense. We want to shut the process down if we're in an energy-rich state. Okay, another one. Let's say that we have a high, acetyl coenzyme A concentration. Again, are we energy rich or are we energy deficient? You're energy rich. So again, you want to slow the process down, because if we have a lot of acetyl coenzyme A, that means we've got way too much for the citric acid cycle to accommodate. So therefore, we must be energy rich, or you got to be reactant poor. In other words, we must be short on oxaloacetate or something like that. So again, particularly, this inhibits the thiolase. So in other words, the thiolase is what's making, right, the thioester. So in other words, that fat's going into the cell. We're not going to convert it to the thioester so that it can get moved in to do the reaction.
So it inhibits the thiolase, right?
Right.
And for the high NADH, you said that if that inhibits the beta hydroxy.
Yeah, it inhibits that particular enzyme. Right. So I mean, I'm not going to ask you. That's not a good test question, by the way. Right? I'm not going to expect you to know the particular enzymes. But, like I said, what I would expect you to know is what this indicates as far as the energy level and what you think it would do. All right. We got one more, but we'll save it. All right. Okay, so watch. I will send out everything that I talked about.
Jackie,
on the
yes.
pages.
Do you want these
So
notes today, or
we'll
can
get
I
that.
copy them when I get home and give them to you tomorrow?
Okay.
That one's gonna be easy.